So as I alluded to in the previous video, the subdiscipline of analytical chemistry is massive. And there's two big categorizations that we think about, and really is sort of the division even within this class. We think about analytical chemistry in terms of wet chemical skills and instrumentation skills. So we're going to start by talking a little bit about the tools of the trade and specifically thinking about some of the wet chemical tools. So this sort of day-to-day lab-based chemical tools that you need to be pretty well versed in to be successful, not just in this class, but just as a good scientist. So under wet chemistry, as I mentioned in the previous video, we're most often thinking about measuring things by mass in the lab or by volume. And sometimes in wet chemical methods, we'll also think about measuring things by potential or voltage. So when we think about measuring something by mass in the chemistry lab, then we're generally thinking about one of two tools, and many, if not all of you, have used these tools, both of them, in previous chemical labs. So on the left we have what's called the analytical balance, and on the right we have what's called the top loading or top loader balance. Both of these are digital balances, so they've replaced the triple beam analog balances that you may have seen in a movie, but you've probably never actually seen them in real life. I have very, very limited use of them in my life. Well, when do you use these two tools? They have massive price differences. So a typical analytical balance will start you around about $5K. A top loader, I just bought a bunch for you, which you have in your kits, a simple top loader that can go out to 0.01 grams for about, I think I paid $14 a piece. So what's the difference? What are you getting out of these two things? And I think that this points out one of the fundamental questions that you need to develop as an intuition in analytical chemistry: when to use the right tool. Because both these tools will measure the mass of a substance, but when would I use one on the left, when would I use one on the right? So a typical analytical balance would run us around 0.000 x grams, which means we're running out to about 1/10 of a milligram in terms of the readability or the ability to actually measure that value. Whereas a top loader can often, in the cheapest sense, can run into the sort of 1/10 of a gram, but like yours can run nowadays, sensors are getting cheaper, can run out to the 100th gram, and one in my research lab, which cost about $200, can run out to the single milligram. So what situations would you need these different balances? Well, this goes back to what you learned in, say, a general chemistry course, in which we're going to talk quite a bit about in this course, which is, well, how many digits of significance do you need in the analysis that you subsequently do with that number? In other words, am I measuring a number where it's really important to, say, the 1/10 of a milligram, exactly what mass I'm measuring? An application of this might be medicine, right? A lot of dosage is highly dependent upon a very small margin of error, right? Every drug is a poison if the dosage is too high, and every drug is ineffective if the dosage is too low. And so in that case, it's really important that you have the right tool to measure this out to the sub-milligram level. There's also balances out there that can measure down to the single microgram or even sub-microgram level. Those balances, as you can imagine, these are 5K. A microgram balance will run you about 50K starting. We have two of them at CC. In other cases, like if you are simply doing a titration in an analytical chemistry lab, then the instructor may say, well, actually 2 digits past the decimal is reasonable enough for the types of error that we're dealing with. So a huge question that is addressed in analytical chemistry is thinking, what are you going to do with the data when you're done with it? What is its end use? What is the importance of accuracy and precision in the measurement you're conducting? Because virtually any measurement that you're going to do in this class, there's going to be multiple ways to do it. And part of the challenge and part of the development as a scientist and a chemist for you is to be able to choose the right tool and balance cost, time, resources, etc. when you're doing that. The other consideration you need to think about when choosing the right tool for analysis are what are the possible errors that could manifest with my chosen tool. So what are some errors in the analysis of mass in a chemical lab? Well, you could probably think through several of these things. So brainstorm a little bit. Like, what are some of the things that if you're going to go measure an unknown substance, what are things that you would just intuitively consider to do to minimize your overall error? There's a lot of things that you already have intuitively. One might be the temperature. Right? You probably don't want to take your unknown sample that you want to obtain the mass of and have it be really hot or really cold. For a variety of reasons, those things can influence the measurement on one of these balances. Specifically, convection, which is the loss of heat through air movement, can cause this really sensitive pan that sits on this balance to oscillate up and down, which causes the number here in the digit to move up and down, leading to error in your measurement. Other things that I think are probably pretty intuitive to you are fingerprints, believe it or not, but fingerprints have mass because they are composed of oils and whatever junk you have on your hands. And so when you have a vial and you've got a really tiny amount of a product you just synthesized in the bottom of that vial, and then you leave a nice big greasy thumbprint on both sides of this, that's going to contribute to the mass of this object, right? So there's best practices there, which we can talk about, but a lot of them are fairly intuitive, like using gloves, making sure things are at room temperature. Another component that can cause error in mass measurements is magnetic fields. The reason it has to do with how the actual balance works. So you may never have thought about what's on the insides of one of these things. And if you go on to take an instrumental course, Chem 342, we'll talk a little bit about the electronics that goes into making a device like this. But generally, the way this works is you have a metal pan, and this section all here, this is all the stuff inside, and then this is your sample. So generally what you have is an electromagnet, which is a coil of usually copper wire passing a current around a magnet. And that magnet is sitting inside of another static magnet. And so as this mass is added inside of this magnet, this electromagnet, is going to adjust its current so that it sits directly in the center of the magnet. And so if you put a lot of mass on it, this thing is going to adjust and push back upward. If you put a little mass on it, it's going to push backward. That current that's required to reach sort of that middle line gets fed into this, what we call an operational amplifier, and we get some response in our measurement or in our display. That's how this thing works. So as you can imagine, if you take a magnetic object and toss it onto your pan, it's going to wildly interfere with the mechanism that's used to measure this. It's less important that you know that specific anecdote, although it's pretty important since you use balances a lot. But it's more important that you take away what I want you to start thinking about is, well, when I'm measuring a particular sample or analyte, is there anything about that sample or analyte that's going to interfere with the mechanism by which the analysis occurs? In this case, if you have a sample of, say, a chunk of iron or magnetite or hematite, you toss it on the pan, you're not going to get a good analysis of its mass. So you may want to choose a different technique rather than, say, an analytical or top-loader balance. That's the sort of decision tree that I want you to start to develop as an intuition, which will make you a much, much better scientist rather than just simply using whatever tool is available to you and not really thinking about the implications of the use of that tool for your specific sample. So the other standard wet chemical technique is measuring the volume of things. And this is probably one of the first things you were ever introduced to as like a real experiment in a general chemistry course via a titration. Right? So a titration looks something like this picture, where you have this piece of glassware, usually it's set up in a clamp, and there's some fidelity or precision by which you can dispense and control the amount of some liquid, we call a titrant, into a sample below. And normally you're adding either a base to an acid or an acid to a base, and you're using an indicator or a pH electrode to tell you when you reach the end point, or in other words, when the number of moles of your base is exactly equivalent to the number of moles of your acid, right? So that requires some constraint in the type of equipment that we use to measure volume, right? We need to be able to deliver precise and accurate volumes of liquid. And I want to be clear when I talk about precision and accuracy, you may be super familiar with this already, but I'm going to remind you again in case you didn't take general chemistry with me. Accuracy refers to the proximity of a measurement, or how close it is, of whatever your measurement is when you're measuring, to the true value. So to truth. You may not know what the true value is, that's why you might be measuring it, but there is a true value. The universe holds a true value for that measurement, and so for your method, the accuracy is how close you can get to that real value. That's distinctly different than precision or being precise, which specifically has to do with reproducibility. So how well, if you measure, if you do a titration 3 times, do you get the same answer every time, or do you get a bunch of different sort of results? The classical description here is to use a bullseye, and let's just draw 2 of them here, these wonderful bullseyes. If we were to throw darts at this bullseye, if we had the accuracy, the sort of analogy is accuracy is this dead center of the bullseye. That's where the true measurement lies. So if you have an accurate set of measurements, that means maybe I did 5 measurements and I'm sort of clustered around the centroid or the true value. That's an example of an accurate set of measurements. And then for precise set of measurements, they don't have to be accurate, but they can. So this would be an example of, say, 5 really precise measurements. This is high precision, but low accuracy, right? Because they're really, really close together, meaning you're really reproducible, but they have associated with it some amount of what we call systematic error, or error that displaces your clustered set of measurements away from the true value. We're going to talk quite a bit about error in the next few videos, but I just want to give you a quick heads up when I use the terms accuracy and precision when talking about volumetric glassware. This is what I mean by these two. They're not interchangeable. So when you did your first titration, you almost certainly used this thing here, which is called a Buret. And a Buret is this very accurate and precise volumetric piece of glassware, almost one of the most accurate and precise pieces of glassware, which allows us to read difference in volumes very accurately and precisely. And typically we can read volumes out to plus or minus 0.02 milliliters with a standard Buret. You don't need to use this if you're just measuring out roughly 100 mils of something, right? If you need to roughly measure 100 mils of something, then you could use a variety of different pieces of glassware. You could use a graduated cylinder, which will give you a rough amount. Even more rough would be to just use a beaker and fill it up to the line that says 100. Those would be rough estimates of volume. This use of Buret would be a very accurate and precise use of a volumetric piece of glassware. And for that reason, the manufacturing process for this Buret is hard. It's difficult to blow glass that maintains accuracy and precision in delivering volumes to such a high degree. So this is about $150 to $200 for this piece of glassware, whereas a beaker may cost us $1 to $2 for the equivalent measurement, right? And so you're choosing the right tool for the job depending on what level of information you need. If you need 4 significant figures in whatever the outcome concentration is, you're going to need to use a Buret. There's no question about it. You're not going to get that from either of these other tools. One significant component of error that I'll toss in here is, or propensity for error, is that you want to rinse your Buret with the titrant that you're going to use to titrate before you fill it up. that may sound sort of cryptic to you, but what that means is if you're going to load this up with 0.1000 molar NaOH and do a titration, and before that it was either empty or filled with water or something else, you don't want to fill that up and do your titration right off. What you want to do is fill it up just a little bit with your titrant, put a cap in it, and then invert it back and forth so that there's a thin layer of your solution on the inside, then drain it, then close the stopcock again, and then re-add your titrant up to the middle, or up to your zero line, or wherever you want to start. And the purpose of that is if there's water in there, it's going to dilute it. Even a little bit is going to add air to your system, and sometimes that air, even if it's small, is intolerable depending on the application, especially if it's medical. And another enormously valuable tool that you'll actually use in your lab kits, but it's just a standard in the chemist's toolkit, not just the analytical chemist, but any chemist, would be this thing called a volumetric flask. So a volumetric flask, and all of you have used this before if you took Gen Chem here, but you may not have thought through the details. This is another precision blown piece of glassware. It's expensive. And the benefit of a volumetric flask is it has a pre-inscribed mark that very accurately determines what the volume of a solution will be inside of it. And so the application of where these are often used, or almost always used exclusively, is when you need to make a solution with a very accurate concentration. So say you need to make a solution at 1.000 molar, say sodium chloride, and you want to do that in 500 milliliters. You're going to grab a 500 milliliter volumetric flask. You're going to go and weigh out a half a mole of NaCl, so 0.5000 moles of NaCl. That'll give you 0.5 moles per 0.5000 liters, and that will give you 1 molar. The cool part about using a volumetric flask is some amount of the volume is going to be taken up by the mass or the size of the solid itself. So you're going to put this in the bottom. You don't have to account for that at all, because what you can do is just toss that mass in there and then bring up the solution all the way to 500 mils. And now your solution has exactly 500 mils, which is exactly what you want. The opposite of this would be to take a beaker, toss in your mass into the bottom, and then take another measurement technique, maybe a graduated cylinder, take 500 mils of that and pour that into here. These two things are not equivalent to each other, because this thing, this amount of NaCl, is going to take up some room, and you're not accounting for that because you're adding 500 mils. In this case, you're not necessarily adding 500 mils, you're adding some amount a little bit less than 500, which automatically compensates for how much of the mass you started with. This is the beautiful utility of a volumetric flask and why we use it to make virtually all solutions, because it's the only way that we can be absolutely certain of what concentration we're trying to make up for a solution, knowing that when we talk about the molarity of a solution, we are referring to the solution, right? That's going to be moles of solute per liter of solution, and that's why it works when you're talking about molarity. When you talk about units like molality, then this second method is an easier approach. But we won't do anything with molality in this class. All right, there are several other types of equipment. I won't cover them in detail for volumetric measurement. You may have used some of these. You may have seen some of these around. So we have the standard Buret, which is sort of the best way to get really accurate and precise volumetric deliveries of a liquid. We also have these things with called volumetric pipettes, which are sort of similar to a volumetric flask, but instead of being in a flask, they're sort of pre-set to a size that delivers an exact volume. These are really nice. One thing to note regarding error is the tips of these things are designed and calibrated to leave the last drop. So you don't want to blow these out. If you have a pipette bulb here and you expel air to blow out the last drop here, then you're going to have additional volume that wasn't calibrated for. So it's meant to leave the last drop. For really, really small volumes on the order of 1 to roughly 1,000 microliters, we use these things called glass microliter syringes. They look like a needle with a glass bore and a barrel and a stainless steel plunger. These are awesome. They're gas tight, but they're really expensive, but it's necessitated by these very small volumes. These auto pipettes here are also good for small volumes, 1 to 1,000 microliters, where you need to repeat the same measurement multiple times. You'll see these in molecular biology and biochemistry labs where you're creating cell media or doing identical assays on multiple samples. So this has a spring inside here, so it'll just retract. So you'll depress it with your thumb and then it'll retract, and you can make these repeated measurements with a disposable plastic tip. Problem with these things is they're often horrendously inaccurate, both from an accuracy perspective, but also from a reproducibility perspective. So they're good if you are okay with inaccurate measurements, but repeatable measurements. Otherwise, you need to go through a detailed set of calibrations that most often users don't do. So this is a huge contributor of error if you don't think about it. The last thing about error in measuring volumes is often you have a set indicator or mark, and the question is, where do you fill your liquid up? And so when you fill your liquid up, you're looking for the meniscus, which is caused by the surface tension of water. And one good way to do that is if you're looking at the neck of, say, one of these flasks here or a Buret, the meniscus, the black line that I've got drawn here, should be between the front of the mark, which is on the front of the glass here, and the back of the mark on the back of the glass if you have a transparent solution. So you're sort of looking down at a 45-degree angle like this on your flask, and instead of having two lines that are perfectly parallel to each other and overlapping, you have them create this little oval, and your meniscus can cut right between them. If you're looking at it directly side on, then you'll have your mark, the front mark and the back mark will look the same, and your meniscus should just touch the top for the least error in the volumetric measurement.